Hello, in this video we'll be looking at how a PWM signal is generated and how we can get the duty cycle to change. So I'll be showing a simulation with a high duty cycle and a low duty cycle, and we could get anywhere in between. And this simulation will show us how we can create a PWM signal from a comparator, a sawtooth waveform, and also a varying DC voltage. These types of PWM signals are used in motor control and SMPS, switch mode power supplies, and of course they have other uses. Okay, so I've been looking on the internet for a good pulse width modulated simulation, and I haven't been able to find any as such, so I decided to do my own simulation. And a pulse width modulated signal, that is changing the duty cycle of the pulse width high to low, low to high, is usually a control that is needed in switch mode power supplies or motor controllers, as well as maybe others. Now, the thing about it is that you have to generate the pulse width modulated signal. And to generate it, what we do is we take a sawtooth waveform and compare it to a varying DC voltage, and that gives us a pulse width modulated signal. Let us just look at a graph so that we could understand what's happening. This is our sawtooth waveform here in red. This is our blue DC voltage, which would vary up or down the sawtooth waveform. The comparator would compare whether the sawtooth is higher or lower than the voltage, than the DC voltage, and therefore it would compare and give an output which varies with the duty cycle, or the duty cycle varies at the position where the DC voltage rides on the sawtooth. So this here shows a high duty cycle, and watch where the DC voltage is. This one shows a low duty cycle, and again look at where the DC voltage is. So let's go back to our simulation and see if we could get the simulation to actually run. So I started the simulation here, and our oscilloscope will show us the waveforms, and I will show you that when we reduce the control voltage, the duty cycle becomes higher, and conversely, when we increase the control voltage, the duty cycle becomes lower. So as it is right now, the DC voltage is riding high on the sawtooth, and the duty cycle of the PWM is low. So let's bring the control voltage down, and as we do that, we should see the duty cycle of the PWM increasing. So the simulation needs a little time. And there we have it. We could already see that the duty cycle is increasing as the DC voltage drops. Okay, so we could see it happening. I'll just send it up. I'll just send the control voltage up again a little, and we'll see the opposite, the reverse. That's happening. Again, the simulation needs a little time to run. Okay, so the control voltage goes back up, and the duty cycle of the PWM decreases. So I'll stop that. If the voltage on your SMPS, the output voltage is too high, this means that the control voltage coming from the transformer, from the secondary of the transformer, or the output, is too high, as we see here in this graph. Then this tells the PWM to go to a lower duty cycle. This happens naturally because of the way the circuit is built. And this lower duty cycle controls the primary of the power supply, the SMPS power supply, and hence the output is lowered naturally. If, on the other hand, the output of the SMPS from the secondary of the transformer is too low, as we see here in this graph at the bottom, then what happens, this naturally produces a pulse width modulated signal with a high duty cycle. So this PWM, which is now fed into the primary of the SMPS, the power supply, naturally now tries to raise the output. So this is a natural way, because of the way the circuit is set up. This is a natural way to actually get the power to self-regulate, the power supply to regulate itself through a PWM control. So I hope this has helped somebody.